All right, let's try to evaluate some limits. In this case, we're trying to find the limit as x approaches 5 for this rational function. So I'm getting started here. This one does not come in factored form to us. So a lot of times starting out, what we'd like to do is simply try to evaluate this when x equals 5. So replace each one of the x's with 5s and see what happens. A few different things could happen in this case. But let's take a look at this case. All right, so each one of the x's gets replaced with 5. Then we do a little bit of simplifying down. It looks to me like we're going to get 25 minus 40 plus 15 over negative 35 plus 35. So in this case, it'll work out to be 0 over 0. Well, that actually is helpful. We can't say it does not exist because both the numerator and denominator equaled 0. So my next step on this would be, let's try to factor as much as possible. All right, so thinking about factoring, the limit stays the same for now. The denominator looks like it'll be negative 7 as a common factor, x minus 5 on the inside of that set of parentheses. Because the numerator equaled 0 when we replaced each of the x's with a 5, that kind of tells us that x minus 5 should be a factor up here. Sometimes that helps out in sort of working backwards. That our other factor is going to be x minus 3. All right. Now that we see that we have an x minus 5 in the numerator and denominator, we can put this in lowest terms by eliminating that common factor. And that kind of came from the 0 over 0. We sort of knew that we were going to be able to find a common factor between numerator and denominator. So what that's going to do for us is finding the limit of that big rational function at the beginning is going to be equivalent to finding the limit of the smaller rational function that's been put into lowest terms. All right, so now back to replacing the x with 5, we get 5 minus 3 over negative 7, which will be 2 over negative 7, and that's going to be our limit for that big rational function at the beginning. Works out to be negative 2 sevenths. All right, let's try something similar with this next one. The limit as x approaches 2 of x squared plus 3x plus 3 all over x minus 2. The first thing I'm going to try to do is replace each one of my x's with 2's. Now in the denominator, that's going to make 0. But in the numerator, we get 2 squared plus 3 times 2 plus 3 works out to be what? 4 plus 6 plus 3 all over 0? Or 13 divided by 0. Because we did not get a 0 in the numerator this time, I'm not going to be able to factor that and find an x minus 2 to simplify down to lowest terms. So what this tells us is when it's a number divided by 0, and the number is not 0 divided by 0, this does not exist. All right, let's try another one. I'm going to approach it the same way. We're going to first try to plug in 0. So we get 0 plus 7 over 0 squared plus 9 times 0 plus 14. Simplifying this down, we'll get 7. 0 plus 7 is 7. And then for the denominator, 0 plus 14 works out to be 7/14, which is 1/2. So no further reducing down needed. This limit simply equals 1/2. And then finally, one more here. Let's take the limit as x approaches 1 of x squared minus 1 over x squared plus 1. Approaching it the same way, we're going to replace each of the x's with 1. So we get 1 squared minus 1 over 1 squared plus 1. So 1 minus 1 over 1 plus 1 is 0 over 2. This time we got a 0 in the numerator, but 0 in the numerator is okay. 0 divided by 2 ways is still equal to 0. That's not a does not exist case. Does not exist occurred when we had a number that wasn't 0 divided by 0, as we saw up above here. All right, so I hope this helps out as you're working on limits. First, try to replace each of the x's with whatever number your x is approaching. Then if you get 0 over 0, as we did in that first one, you want to think about factoring further, putting it into lowest terms, and then reducing down. Good luck.